Well, we're rolling right along. This is the fifth of 6 videos on characterization of organic compounds. And we have looked for the last 4 videos at either taking in a structure and elucidating or determining what the theoretical spectrum might look like for that structure by proton NMR spectroscopy. And in the last video we did the harder task, really not using any new concepts but just applied to a different problem. We started with spectra, and with some information about the molecular formula either through mass spectrometry or just given, we can take spectra and mass and molecular formula and determine a structure that fits the data. And we really still looked at those 3 issues of number and position of peaks, integration, splitting. But when we went spectra back to structure, remember, we really started with integration. It was the most, secure bit of data you can start working with in the proton NMR spectra. So integration, then splitting, and then position of peaks. So we're on our 5th, video, and we have one more after this that'll deal with mass spectrometry. Well, let's cover, in this video, we're going to cover as quickly as we can just the basics of C13 NMR spectroscopy. Why do we, use it? What's its advantage over proton NMR spectroscopy, or what's its disadvantage? And then just talk about, very briefly, the basic phenomenon needed for infrared spectroscopy and data analysis. So let's look at C13 NMR compared to proton NMR spectroscopy. And we're going to take this alkane that's just been chlorinated on the very end here. So we have pentane, 1-chloropentane, 1-chloropentane that we've proposed here. So we're kind of working from the structure here to what the spectra might look like. And just as a quick review, you know that these carbons are not chemically equivalent, though they'd be very, very similar on this tail end as far as their properties. Alkanes far away from this halogen by inductive effects, just can't reach out and affect or influence this end. These would be very, very similar over in this region as far as chemical properties. Magnetically, these would be very, very hard to resolve by NMR because they are interior alkyl groups. At least the terminals tend to be a little bit below 1 in NMR, but these would be falling on top of each other. And we sort of see that in the NMR with proton NMR. So this proton NMR, we can see that the number of signals we have does not match the number of non-equivalent protons. Non-equivalent protons, we have these in blue and red, but we also have, because of their position to the chlorine, these are non-equivalent protons. So you'd expect 1, 2, 3, 4, 5 signals. You look at the proton NMR, 1, 2, 3, 4 signals. What gives? Well, it's just the problem of having protons that are just too similar. They're not exactly similar, but these 2 sets here, these 2 and these 2, just have signals that are very, very close and just cannot be resolved. Probably underneath this signal here, we have 2 signals just overlapping. So we can argue that the one that's most downfield would be for these 2 protons, and it seems to show a triplet. A triplet seems to show a triplet, and it would be explained by being next a proton on a sp3 carbon that's bonded to a heteroatom, as we said in the last slide. So we'd say that's in the 2.5 to 4.5 range, and certainly falls there. And we'd say these pendant methyl groups tend to fall in just below 1, and we'd have a simple splitting, a triplet, with maybe some, again, leaning towards whatever it's split with. But this is below 1. It's certainly most likely representing these 3 protons here. And we could argue, kind of coming from the downfield side again, that this signal here is really due to these protons that are feeling some sort of residual inductive effect of the chlorine. Again, this chlorine pulls on this carbon, and therefore this carbon is partially positive, which pulls on this carbon, and maybe that effect sort of tapers out when we get down to this point, but still affects this set, or these 2 protons. That might be this signal here. So we have A, B, C, and D protons, and then E, we could say, is for these 3 here. we could say that's a problem, because if, of course, proton NMR, we would like to have all signals resolvable, all non-equivalent protons having their own signal, but this is really two signals overlapping, and it's of course hard to look at splitting if two signals are on top of each other, so you want to separate them all. Well, that can't be done sometimes with NMR, and you can say, well, I'll just get a bigger magnet. Well, sometimes your molecules get bigger and it becomes harder and harder to resolve peaks if you have a very large structure, regardless of the strength of your magnet in proton NMR. But carbon runs on a much wider ball field, so you can have your signals stretch from 0 to anything up near 100 ppms. You can have your signals spread out, and if you decouple, meaning you don't look at splitting of carbons by other protons or carbons, we can have just nice, what we would say, sort of singlets. I don't want to use that term because we're not looking at coupling with most C13 NMR programs that you use on the instrument. They're already set to decoupled C13 NMR, where you're just looking at the number of signals representing the C13 nuclei, and you're not looking at splitting. You're just looking at the non-equivalent number of carbons in that structure is going to match the number of signals. So number of signals is going to match number of non-equivalent carbons. So that's just something that's just nice, that you can look at the C13 NMR spectra and determine the number of non-equivalent carbons, because it's very rare that signals would fall on top of each other. The number of signals is the number of non-equivalent carbons, because they just have a much wider ball field for those signals to fall on, so to speak, and you just decouple, so you have just sort of intense, I don't want to, just peaks that represent each carbon. So let's kind of summarize the differences. The number of different carbons is easily discernible. Sort of made the argument for that, 0 to 120 ppms, 0 to 10 ppms for proton NMR. There's no splitting and integration. Well, it's possible, but it's just usually not done. And one of the reasons we don't really look at integration much is because we have C13 as the isotope we're looking at, much less significant as percentage-wise to the number of isotopes. The C12 isotope is very common, so you typically don't do integration, and we just typically don't do splitting for C13 NMR analysis. Lastly, signal location is determined by same things that set it for proton NMR: electronegativity and pi bond effect. So you do see a downfield shift if we consider the electronegative group. So we can really take these signals here, 5 of them, 1, 2, 3, 4, 5. 5 types of carbons, 1, 2, 3, 4, 5, and say this one on the left, closest to the left side, the D-shielded side, is for this A carbon, not the protons. We're looking at the carbons now. A carbon here, because it's bonded to the chlorine, and then B, and on down the line C, D, and E. We can simply say, because of the chlorine's withdrawing effect, de-shielding effect, those that are on the left would be closest to the chlorine. Those that are on the right would be furthest from the chlorine. Right, you do not need to memorize C13 and more chemical shifts. In most cases, you're just asked to sort of understand the trends and understand that the number of signals is equal to the number of non-equivalent carbons. So just to kind of flush this out even more, it's just taking a more complex structure, camphor, and this is the proton NMR. You have a lot of alkyl protons, protons on carbons that are sp3 bonded to sp3 carbons. So you get a lot of noise in that 1 to 1.5 or a little bit higher here too. You see the carbonyls effect, but a lot within that sort of 0.5 to 2.5 range. We have a lot of signals. Now certainly C, B, and A we can resolve fairly well, but we have a lot of other signals that can't be resolved well. But we take that same molecule and we look at the C13 NMR, very nice resolution. We can take and determine that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different carbons. And you can check that. We can find that we do have 10 different carbons within camphor. So it's really nice resolvable peaks in terms of the determination of the number of non-equivalent carbons. Does that match up with this? Well, it certainly does. So all of these on the ring, I'll just go ahead and go through it real quickly. On the ring, there's a 6-membered ring, 1, 2, 3, 4, 5, 6, are all resolvable because are all this non-equivalent because we have so many points of reference. We have this is different from the other side, and the carbonyl group. So 1, 2, 3, 4, 5, 6. So we're trying to get to that number of non-equivalent carbons to be 10 because we had 10 signals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we can count the number of carbons. 1, 2, 3, 4 that are off that 6-membered ring. So 7, 8, 9, 10. And so we can, I guess, remember you do get a peak down. This CDCCl3 can sometimes show up right at 80, so we don't see that here. So these are from the sample. So 10 signals. We had 10 non-equivalent carbons. That's a match. This confirms that we do indeed have, or at least gives indication that we do indeed have camphor. And we could do even position where they fall. You could look at this one down at 220 is going to represent the carbon at 1 here, and you can look at tables to see if it matches up with in the table where they should fall, those 10 signals. Well, that's it for C13. Just remember the number of signals is equal to the number of non-equivalent carbons. That's the really big take-home message for C13 NMR analysis. IR analysis, just going to go very quickly through the basic phenomenon. It's all about the vibration. It's not initiating it. It's about exciting it. That's what IR light does. Infrared light excites vibrations. We use the infrared range just below the visible spectrum of 380 nanometers to 780. We use the light that's lower in energy, just on the lower end of that visible light, to excite vibrations. We are using this light not to excite magnetic flips like an NMR, but to excite vibrations. What types of vibrations? Well, there's really two basic types, and I have a little model here for this. One's of a higher energy. It's going to be on the left side of the IR spectra, what we call the high energy side. So high energy or higher energy, and the cutoff is sort of around 1600 wave number. This is just a measure of the wave number or the energy in a different way. We usually have frequency and energy. Just wave number is a different measurement of the frequency of light. The high energy side, the low energy side. And around again 1600 is our dividing line. Typically above 1600 reciprocal centimeters or wave numbers, we have stretching modes that are excited. Stretching modes, if I were to look at my spring here, would be this type of mode. And it is, if you try it on your own with any spring, it's a harder move or action to stretch a spring. But if we take that same spring and bend it, oh my land, I can get a lot of displacement there. I cannot, I could really pull this thing perfectly straight. That's how strong I am. Now I'm pulling pretty hard, and I'm getting a little displacement, but not a lot. But here, oh my land, I can displace it very easily. That's a bending mode of vibration. Bending mode. So bending is a low energy vibration that we're exciting, not initiating. It's not like the bond's still and then starts to waggle when we hit it with light. No, it's already waggling. I mean, our molecules are moving and grooving. But we're just exciting that bending mode from one vibrational state to a second vibrational state. And of course, because this is in a quantized state, these vibrations, we have to have chunks of energy added to go from one bending mode to another bending mode. You have to have a set amount of energy, which is a set amount of light, or energy of light, which gives us particular wave numbers. So let's look at some particular wave numbers. Well, we have particular wave numbers that fall in for stretching modes that we excite for OH groups, and it's typically a broad signal because we can have hydrogen bonding. Hydrogen bonding makes these broad. The less hydrogen bonding, the more narrow this peak is. So that sometimes tips you off as to how much hydrogen bonding you have. And if it's in a carboxylic acid, which you get a lot of hydrogen bonding in, because you can have an OH from another carboxylic acid sit right across from the oxygen of a carboxylic acid. You get a lot of good sort of molecular interactions. We get a very broad signal from 2,500 reciprocal centimeters to 3,500 reciprocal centimeters, roughly about 1,000 wave numbers wide. A very wide stretch, so broad. This is one you should know. The OH stretches centered around 3,000 if it's for a carboxylic acid, centered around 3,300 if it's an OH group. Now CH stretches, we have a lot of CHs within organic molecules, a lot of carbons and bonded to hydrogens. So you should know where those fall. If it's an sp2 carbon, as we're showing here, sp2, the carbon has a hybrid orbital that's lower energy reaching out to bond to this hydrogen. It's an sp2 hybrid orbital bonded with this hydrogen. That gives you a stronger bond, excuse me, higher energy vibration, just above 3,000 reciprocal centimeters. And if it's sp3, yes, guess what? It's just below, a little lower energy. This is really nice. We'll see as we look at data. You can find the 3,000 mark and look to the just to the high energy side or just to the low energy side. You often see these stretches. And lastly, just know in general that the double bonds between C and O have a lot of different types, but they generally fall very strong signal, not too broad, fall from 1680 to 1850 reciprocal centimeters. And then the triple bonds between carbons, this is a weak signal because polarity determines the intensity of the signal. This is not a very polar group, but if you have a greater polarity in the group, it tends to give a stronger signal, stronger, I should say medium strength as far as compared to others, like the carbonyl. It's very strong. Strong meaning very intense. Medium intensity, very weak signal if it's an alkyne. And then if it's a cyano group, a little stronger. And they fall in around 2100 to 2200, those two. So know where those two fall also. Let's just go ahead and look at some data and work through some ideas as we look at the data. Now, unlike proton NMR, you're not going to be doing peak analysis to see neighboring effects or resolve each of these signals as indicating something about the functional group. You're just going to sort of look at where signals in general fall. So I'm going to just kind of point out that 3,000 mark here and say we have some peaks that look like to both the left and the right of that 3,000 mark. This would seem to, I guess, fit with the fact that we have two types of CH bonds, those off of sp2 carbons and those off of sp3 carbons. So we expect that. And again, we're not analyzing the profile here, we're just sort of saying we have some peaks around 3,000 that might indicate the presence of CH groups. And it's not that these individually, these stretches are very sensitive, but just usually have a whole lot of CH groups, so it tends to give you a fairly strong signal. But we also see this broad signal centered around, looks like 3,300 roughly, a little bit higher, 3,400, 3,300. So hey, that indicates I have an OH group, and it's not in a carboxylic acid. That would be centered around 3,000 in a very broad signal. It's centered around 3,300 roughly. So that indicates an OH group is present. And so we could say, just from the data, I'm thinking there are some CH groups, and I have an OH. Now we don't typically, again, do analysis of peaks in what's called the fingerprint region. This is the fingerprint region, and this is the functional group region. And as you've just seen, we've been looking at signals and saying, hey, I think I have a certain functional group, an sp3 carbon stretch indicated here. Maybe this one right here indicates a sp2 CH stretch, and this represents an OH group. That's functional group region of the NMR spectra, or IR spectra. This is sort of the fingerprint region, again using 1600 as our divide. This is the stretching modes and the bending modes. High energy, low energy. And so fingerprint regions are used just like that as a fingerprint. So if you have data for a lot of different compounds, you can match up your spectra with the database and see if there's a 99% fit of the fingerprint region to something in your database. That's how you can use this side, because you have a lot of peaks down there, a lot of signals, a lot of different bending modes that we can use to match up with some database. Now let's check out, I guess we have a carbonyl. We can say, oh, that's a CO. That's that one that shows up 1680, so 1860. Very strong. Oh, that's it. I can label this peak as indicating the presence of this functional group of carbonyl. We look at our 3000 again, and it looks like most of what we have is to the south of 3000, the low energy side, just on the low energy side. So I expect then that I have a lot of CH stretches involving sp3 carbons, sp3 carbon hydrogen bonds. So carbons sp3 hybridized bonded to hydrogens. Yeah, I have a whole lot of them. We've got 2 methyl groups here, we have a methene group here, and we have, I guess, indicate some of those that we've needed to memorize present within this structure. And again, we have our functional group fingerprint region, which we could try to match up if we wanted to with the fingerprint for this exact structure. That's just kind of the game you play. And again, I don't have that you memorize all. We could look for this one from the table, but we have these two, the sp3 carbon hydrogen bonds, around 3000 just to the low energy side. The carbonyl groups, very intense peak, usually the strongest one if we have it, and that's from that 1680 to 1850 range or whatever. Alright, one last thing, just kind of a neat story. If you look at carbonyls and their vibration mode, their stretching mode, tends to be affected by groups nearby in this way. If it's a donating group, electron donating, tends to take the carbonyl's vibration to a lower energy, tends to make that lower energy vibration. We can say it's due to sort of since the breaking of the pi bond, and through a resonance form we know this lone pair is donated to the carbonyl, sort of weakening the strength of the pi bond between the C and the O. So we can say we have a lower frequency of vibration for the stretching mode of this CO bond if we have electron donating groups. And of course, you can think the opposite. If we have electron withdrawing, a higher energy, higher frequency. So we tend to see that. We look at the amine next to a carbonyl, and we see 1653 reciprocal centimeters. But if we go to, I guess over here, we'll just say the non-withdrawing, just alkyl groups around it. 1715, sorry, should be a dot there, a decimal. We see around 1720 for just having R groups to either side. Now it's interesting, a lot of students from organic chemistry would say, well, isn't this able to donate its lone pair down to the carbonyl and thus give us a resonance form? Well, I hope you realize that we can't do that here because we can't line up the p orbital, if you were to try and make this sp2 hybridized, with the p orbital that's coming straight out towards you. If these two are in the plane, the pi bond is involving p orbitals that are coming straight out towards your eye. Well, this is going straight up into the plane of the paper. These are coming out of the plane. So you just can't donate by resonance the lone pair. So resonance is out and inductive effects is in. So this is still withdrawing. So that increases the frequency of vibration for the carbonyl. So I just thought it'd be a little fun story here to tell, because most students would think, oh, nitrogen next to a carbonyl, donating, I'm going to have the same low energy vibration that I see over here. But because of the ring strain, I can't rotate this orbital around that would hold the lone pair so it overlaps with the two p orbitals here. It's locked out in this bidentate structure. So we have a higher frequency the highest frequency because it's an electron withdrawing group now, because it can't give by resonance, but it still takes by inductive effect. And that's it. That's just a neat story. This twisted amide here, this stretching frequency is actually higher than that for the amide here. That's it. Bye-bye.